In this video, we're going to learn to use VSEPR theory to predict the shapes of some molecules. Remember that the key feature of VSEPR is that it says that bonding electron pairs and lone pairs repel, so the molecule will try to arrange itself so that the electrons are as far apart as possible. To explore this, I'm going to work through 3 examples of basic molecular shapes. For each one, we'll look at a specific molecule, and I'll first get you to draw the Lewis structure, so have a pen and paper handy. I'll then get you to pause the video and think about how the bonds in that molecule could arrange themselves to minimize the repulsion between the electrons in neighboring bonds. In other words, what's the best shape for this molecule so that the bonds are as far apart as possible? Let's start with carbon dioxide. First, pause the video and draw the Lewis structure for this molecule. Remember to tally up the valence electrons in all the atoms first. Okay, so hopefully this is what you drew. If you got it wrong, go back to the material from Unit 1 on Lewis structures and do a bit of revision, because it's almost impossible to draw VSEPR structures without first being able to draw accurate Lewis structures. So the question now is, how can the bonds position themselves so that they minimize repulsion? Note that for the purposes of VSEPR, we count each collection of bonding electrons as essentially a single bond. And by this I mean, although there's a double bond joining the carbon to each oxygen, we're not trying to separate out the 2 bonds within each double bond. Those 4 electrons are strongly localized in between the carbon and oxygen atoms. What we want to know is, where can the 2 oxygen atoms sit so that the 2 double bonds are as far apart as possible? For 2 bonds like this, the answer's fairly easy to visualize. They have to point in opposite directions. If you were to move either oxygen out of line, it would bring the carbon-oxygen bonds closer together. So for CO2, the VSEPR drawing looks just like the Lewis structure, and we can indicate that the bond angle, that's the angle made by these 2 bonds, is 180 degrees. This molecular shape is very sensibly called linear. So far so good. Alright, let's try boron trichloride, which you had to think about at the end of the last video. First, pause the video and draw the Lewis structure for this molecule, or you can get your working from when you did it before. This is what you would have drawn. Remember that boron is one of those funny atoms that can happily be electron deficient, so it doesn't have a full octet. So, how can the bonds position themselves to minimize repulsion? Well, in this case we've got 3 bonds. If we draw 2 of them linear, then the third one will have to point out at 90 degrees. Is this the best that we can do? What if we shift them around to even the spacing out? Hopefully this is what you predicted in the task at the end of the last video. This molecular shape, with 3 bonds spaced out like a propeller, is called trigonal planar, because the bonds point to the vertices of a triangle, and they're all in the same plane, so this molecule is flat. The last detail to add is that if the bonds are evenly spaced, then because there are 360 degrees in a circle, the angle between each pair must be 120 degrees. Okay, now let's try methane. I expect that you can all successfully draw the Lewis structure for methane by now, so let's skip to the chase. How can these 4 bonds minimize repulsion? Perhaps they stay planar, just like the Lewis diagram. Then there'd be 90 degrees between each pair of bonds. But is there nothing that we could do with this to space them out a bit more? We haven't yet used the 3rd dimension. If we move things around and let 2 of the bonds point forwards and back, then we can come up with this shape. Imagine a triangle-based pyramid or tetrahedron. This molecule has the carbon at the very center of the pyramid, and the 4 hydrogens are at the 4 vertices. It's just like the chloroform molecule I drew in the last video. This shape is called tetrahedral, and the bond angle between each pair of bonds is 109.5 degrees, which you can see is an improvement on 90 degrees. The bonds are definitely further apart this way than if the molecule was squashed flat like it looks in the Lewis structure. But what's with this drawing here? What's with the weird looking bonds? Well, this is where I have to introduce you to wedge-dash diagrams. This is a simple way of drawing molecules so that you can indicate the 3D structure. For methane here, the wedge shape indicates that the bond should be poking out of the page, while the dotted bond is receding back into the page. The other 2 bonds, drawn as ordinary lines, are in the plane of the page. Anytime you need to draw a molecule that isn't planar, you can use wedges and dashes to show that. So to summarise, we've seen three basic molecular shapes: linear, trigonal planar, and tetrahedral. And it's the number of bonds that there are to arrange around the central atom that determines which one occurs. In addition, each shape has a characteristic bond angle which directly depends on the geometry. You can see the pictures of the balloons here represent the electron clouds that are the bonds, and it's showing how they can arrange themselves to minimise that repulsion. I should say that this doesn't represent all possible molecular shapes. Obviously there are many more complex ones. We're going to look at some variations on those shapes. So let's start with ammonia. First, pause the video and draw the Lewis structure. You would have come up with this. So how do you think this molecule would arrange its bonds? Well, it has three of them. So it might seem logical to say it's like the boron trichloride that we looked at in the last video. It's trigonal planar. But when you do crystallography on ammonia, you find out that actually the shape of its molecules is like this. So what's going on? Well, the main thing that differs between boron trichloride and ammonia is that the ammonia has a lone pair on the central atom. Could that make a difference? Well, the answer is yes, it can. Non-bonding electrons are still negatively charged and can exert a repulsive force just like bonding electrons. So if a central atom has one or more lone pairs, those electrons will compete for space around the atom as well. In effect, they act like a phantom bond. So rather than thinking of ammonia as being based on a central atom with three bonds around it, which would make us think of a trigonal planar shape, we need to think of it as having a central atom surrounded by three bonds and a lone pair, a total of 4 electron groups. And this makes it more like methane, with a tetrahedral geometry. But although the lone pair here is drawn like a giant balloon, it actually doesn't stick out like that. The lone pair repels the other 3 genuine bonds, pushing them closer together, but it doesn't take up space like the hydrogen atoms do. This means that the shape of the molecule is like a tetrahedral molecule with the top bond chopped off, so like a little pyramid. There's one more thing. If you look at the bond angles in ammonia, they're 107 degrees. Do you remember what the bond angles were in methane? An undistorted tetrahedral molecule like methane will have bond angles of 109.5 degrees. Instead, ammonia has slightly smaller bond angles, 107 degrees, which means the hydrogens have somehow been drawn closer together. What could cause this? Well, the inference that we make is that a lone pair exerts a greater repulsive force than a bonding pair. This means that if you had 2 lone pairs repelling each other, the force would be greater than if you had a lone pair versus a bond, as we have here, and that would be greater than the force between 2 bonds. So here, the 3 NH bonds lose out a bit and they're pushed closer together by the lone pair, which makes the bond angle smaller. So ammonia, with 4 electron groups around the central atom, is based on a tetrahedral geometry, but one of the groups is a lone pair, so it doesn't show up in the final molecular shape. Which leaves us with a sort of truncated tetrahedron, which we call a trigonal pyramidal molecule. And to draw that VSEPR structure, you use a wedge and a dash to show the 3D shape and the lone pair so that you don't forget what's making it that shape in the first place. Now let's look at water. Here's the Lewis structure, and again we ask, how can the bonds arrange themselves? Having just looked at ammonia, you may have an inkling of what I'm going to suggest here. Try pausing the video and drawing it out. Again, we have 4 electron groups around the central atom, only this time it's 2 bonds and 2 lone pairs. So, the basic geometry is still tetrahedral, but 2 of the 4 tetrahedral arms are now taken up by lone pairs instead of bonds. So the true shape of the molecule is like a V. This type of molecular shape is referred to as bent or V-shaped for obvious reasons. And to draw the VSEPR structure, we simply draw it like the Lewis structure, with the 2 hydrogens bent downwards. Now the funny thing is that this is probably the way that you've been drawing water since the beginning, without really knowing why. Well, now you do. Those lone pairs repel the 2 OH bonds downwards, pushing them closer together and leaving the molecule in that bent V shape. Now, one more interesting thing is that the bond angle in this molecule is 104.5 degrees, which is smaller than that in methane, which was 109.5, and smaller again than that in ammonia, which was 107. And this is the result of there being two lone pairs instead of just one. So those two single bonds are pushed even closer together because of the more repulsive nature of the lone pairs. So to summarise what we've just looked at, methane, ammonia and water are all based on the tetrahedral geometry. But depending on how many bonds and how many lone pairs are on the central atom, the true shape of the molecule can be either tetrahedral, trigonal pyramidal, or bent. Now, VSEPR theory has a shorthand that allows you to summarise the bonds and lone pairs around a central atom, and therefore to see more easily what the molecular shape will be. This is the AXE notation. A represents the central atom, the X's are surrounding atoms, and the E's are lone pairs. So, try this. Which of these three VSEPR shorthand notations on the left matches with each molecule on the right? See if you can pause the video and work it out. So, methane, with 4 bonds around the central atom and no lone pairs, is denoted AX4E0. Ammonia, with 3 bonds and 1 lone pair, is denoted AX3E1. And water, with 2 bonds and 2 lone pairs, is AX2E2. So let's summarise. When you're drawing a VSEPR structure, first of all, draw out its Lewis structure. That's really important. Secondly, work out its shape. Count the number of electron groups, bonds and lone pairs on the central atom. Work out the geometry that it's based on, and then the actual shape. And then finally, if you can, work out the bond angles. Start from the usual bond angle for that geometry, and then account for lone pairs and double bonds, which exert a greater repulsion than single bonds. Sometimes you may not be able to give an exact bond angle, but you might be able to say, I know that this bond angle is going to be, say, less than 109.5 or less than 120 degrees.